So today we'll be taking our first look at astronomical techniques and SETI, the search for extraterrestrial intelligence. And I thought we'd kick that off by looking at KIC 8462852, also known as Tabby's star. This star was one of many observed continuously for years by the Kepler Space Observatory, and it was noticed in late 2015 that there were some very peculiar dips in its brightness that do not match up to phenomena we'd previously observed. Now, while it is almost certainly a natural phenomena, we never like to rule out the idea that strange things might be the result of either errors or artificial tinkering. So it's been suggested it could be a megastructure, a type of very large artificial construct, presumably of alien origin. Now, if you happen to already be familiar with this channel, it will come as no surprise I get asked about Tabby's star a lot. Two of the biggest subjects covered on this channel are megastructures and the Fermi paradox, the question of where all the aliens are. If you're not familiar with these topics, you can click either of the links on the screen right now to pause this video and watch those in new windows. You should also turn on the closed caption subtitles if you're not used to my voice yet. So I get asked about the star a lot, and have since it came out. I've avoided doing a video on it because I don't think it is likely to be a megastructure, and I still do not. And in astronomy and physics, it isn't unusual to encounter strange mysteries that defy obvious explanations, and have to wait years for evidence to become available. It's a bit tedious and frustrating, but you get used to it. I changed my mind both because I have been getting asked about it a lot more recently, and because we do have more information now, but also because I don't think anyone's done a nice, simple, down-to-earth explanation of the situation. Stuff gets skipped for brevity that I think is important to a basic understanding of this phenomena. We don't do brevity on this channel, and while we do aim for simplicity, we do that not by skipping the hard stuff, but by patiently dissecting it into nice, mouth-sized, chewable bits for easy digestion. We'll do that by dividing it into topics for today and future videos. And here are our topics for today, our questions we want to answer. Number 1. What is the Kepler Space Observatory? Number 2. How did Kepler help us find exoplanets? Number 3. What was the anomaly it found at Tabby's star? Number 4. What does this information tell us? Number 5. What natural phenomena might explain this? Number 6. What new info and developments have occurred? And number 7. What sort of megastructure could it be? Now, as mentioned, we've covered both the Fermi paradox and megastructures in detail elsewhere, so we'll be skimming a lot of that. This video will already be long enough you'll probably want to settle in with a cup of coffee and a snack, so if we cover those in detail again, it would just be longer, and we've already spent several hours on each of those topics. Our first topic is the Kepler Space Observatory. This was launched in 2009 into orbit around the Sun. It doesn't orbit Earth, but rather was launched into orbit around the Sun, initially trailing behind Earth and a bit further out, and is now over 100 million miles away from us. It got further behind us in our orbit because it is a bit further from the Sun than us, and the further you are away from a star, the longer an orbit takes. Same as being closer to a star, or being around a more massive star, makes those orbits go faster, which is pretty important to exoplanet hunting, but for the moment means Kepler is a long way behind us. Now, what this observatory observes is pretty straightforward. It is a photometer, which means it measures brightness. In this case, Kepler constantly measures the brightness of roughly 150,000 stars, which sounds like a lot, but it actually is looking at the same patch of sky, and it's a very small patch, about 0.25% of the night sky. That chunk, incidentally, is in between Vega and Deneb. You probably know Deneb as the star that makes up the tail of Cygnus the Swan, and Vega is in the constellation Lyra, both of which are fairly close to the Big and Little Dippers and North Star Polaris. In fact, Vega was the North Star our ancestors used when the Ice Age was ending, and will be again in a little over 10,000 years. Earth has a 26,000-year planetary precession, and at the moment that makes Polaris the North Star, Vega will get its turn again. And it's also where terms like the Age of Aquarius come from, since the Sun appears in the spring equinox of the Northern Hemisphere in one of the zodiac constellations, and that changes every couple thousand years, and right now it's Aquarius. So Kepler tilts its eyes up and looks at that patch of sky year-round, and it just watches for any increase or decrease in brightness of those stars in that patch, which is again about 150,000. Many of these stars have other names or catalog numbers too, but they exist in the Kepler Input Catalog, or KIC. Kepler wasn't looking for new stars, it was observing known ones, but not many stars actually have names since there are so many of them, so it isn't unusual for one to have multiple catalog entries and just get referred to by whichever one was used when the interesting thing about it was found. Then it usually gets a name to save time and confusion. There's a lot of exoplanets, and a lot of them have names beginning with Kepler or Gleiss, and then a number, and that name just tells you the catalog. The Gleiss catalog, for instance, is a catalog of nearby stars originally published in 1957 by German astronomer Wilhelm Gleiss, and has been kept up. And unsurprisingly, a lot of those stars had no other name yet, and were also the easiest to look for planets around. Those will obviously need renaming if we ever colonize them, since a large number of our nearby stars are named Gleiss something or other, and no colony is going to keep that name in abridged form, since it would be like naming your island Atlas or Rand McNally. And there's a handful of these catalogs that almost all exoplanets are catalogued in. Which takes us to topic 2, hunting for exoplanets. Stars dim for many reasons. Ours fluctuates in brightness, and they all do, but a common cause is from an object getting in the way, and a pretty big object to cause a star to noticeably dim, or a pretty close object. Mercury blocks a lot more light than Mars does, for instance, even though it's a bit smaller. Now, to detect a planet this way, you need 3 things. First, you need for its orbital plane to be tilted towards us. You wouldn't see Mercury or Earth blocking sunlight if you were hanging over the sun's pole, so we can't see an exoplanet around a star that's orbital plane is cocked away from us, and that's most of them. People tend to think the solar system lines up with the galactic plane, but they mostly don't. Our own is tilted about 60 degrees off of it. Second, you need there to be a planet there that's big enough or close enough to its sun to block enough light for us to notice it. That's why virtually all of the original exoplanets were huge things the size of Jupiter and close to their sun. Hot Jupiters are just easiest to see. The bigger it is, the more light it blocks. But the closer it is, the more light it blocks, and the more likely it is to be between us and that star. A tiny little planet like Pluto, far away from its sun, is very unlikely to line up with its star and an observer, and is so small and far away that it blocks virtually no light. It also takes a long time to orbit, which is the third thing. You need to look at these stars for a long time to not only see a dimming, but also a repeat of that dimming. Earth would block light to an observer once a year. Pluto would do it every couple of centuries. And until you've seen this periodic dimming at least a couple of times, you can't do much else. Once you've observed it at least twice, preferably thrice, you can take that period and say there's a planet there and it has an orbital plane of so many days, and from that, combined with the star's mass, calculate how far it is from its own sun. You can then take the star's brightness and determine if that planet might be close enough to have liquid water on it instead of ice, but far enough not to be boiling, what we call the habitable zone. If Earth were around a much more massive star, but at the same distance, our year would be shorter. We'd also burn to death because much more massive stars are a lot brighter. A star twice as massive as our own isn't twice as bright, it's more like 10 times as bright. We also wouldn't be around such a star anyway, since a star twice as massive as our own would only live a little over 1 billion years. Our Sun is 4.6 billion years old, and the Sun was a good 4 billion years old when the first animals started emerging, and not complex ones either. The sea sponge is usually considered to be the first animal. So we don't just look for planets around distant suns. We have, after all, found thousands of them in the last decade. We look for planets in the habitable zone of each system, and Kepler's method, which is just one of the exoplanet hunting methods, is a pretty good one for those hunts. If, for instance, we detected a drop of less than 1% in a star's brightness for a day or so every 750 days around a star about halving in our sun's mass, and about 5 times brighter, we'd know there was a reasonably Earth-sized planet hanging out at about 1.8 astronomical units, AU, 1.8 times further from its sun than Earth was, and that the planet in question would get about half again as much light as we do, in terms of sunlight per unit area, meaning it would be pretty hot, but maybe habitable. We wouldn't much care about one blocking more than 1% of light because it would be too big to be potentially habitable, and one blocking a lot more than 1% would presumably be huge. Indeed, way too huge for even a gas giant if it were orbiting that far out. And when you're collecting data from 150,000 stars each day for years at a time, you're not looking at the raw data. You have a computer shuffling it for the stuff you want. So that takes us to topic 3, the anomaly around Tabby's star, because it is half again our sun's mass and about 5 times brighter than our sun. We detected this anomaly twice, a dip in brightness of 50% the first time and 22% the second time. The first was in March 2011, and the second in February 2013, with a spread of about 750 days. Kepler was launched in March 2009, so we just missed a chance to see it then, and the observatory was having problems in April 2015, so we missed that chance too. We get another in May of 2017. But the dip was huge, and not what was being looked for, since it is most definitely not an Earth-sized, habitable zone planet. With that period, it would be closer to Venus than Earth in how much light it gets, and it would be a lot bigger than Jupiter. The second bigger dip was also very irregular, dimming and then very slightly brightening and dimming way more, something you might expect off a double planet or a coincidental conjunction of 2 planets at the time it was transiting its star for us. So nobody noticed it before the third occasion would have happened, and it was actually volunteers, citizen scientists they've been getting called, who poured through the data manually in the Planet Hunters project. Citizen scientist is a newer term. I would just call that an amateur astronomer, and astronomy has relied on them for a long time. But regardless, I like the initiative to bring more folks into the hunt, and crowdsourcing, for both funds and volunteers, is starting to show up as a genuine alternative to either government or big business research, especially in things like SETI and astronomy in general, and I find this move both fascinating and potentially incredibly useful. I have some friends who started experimenting with research through crowdsourcing for their Space Ranch aquaponics project, and it seems quite promising. It's something I think we'll talk about more in the future, both in regard to SETI and some other projects like that. Anyway, nobody saw it in time for the third dip in early 2015, or we could have arranged to look at it without Kepler, which again was malfunctioning at the time. But once they did, they sent it on to the astronomers, who went WTF, and nicknamed the star the WTF star, which officially was short for Where's the Flux, in reference to the weird flux in brightness, though I preferred What the Flux personally. Eventually, instead of calling it by its Kepler catalog number, or that technically not a curse word cognomen, everyone started calling it for the lead author on the team that wrote it up, astronomer Tabitha Boyajian, or Tabby's star. She's also led the campaign to get funds to observe the star in more detail, and in different frequencies than Kepler did. But that was the anomaly, and again, we just missed seeing it the first time in 2009, right before Kepler went active, and missed it in 2015 from technical problems. So we haven't got much data yet. So topic number 4, what does this tell us? First, as I mentioned, a dip of this magnitude at that distance, a bit under twice as far from that star as Earth is from our Sun, means the thing is huge, whatever it is. Much bigger than Jupiter. Second, it's hotter than Earth, since it gets about 50% more sunlight per unit area. Now I want to mention that Tabby's star is a F3 star, either on its main sequence, or the late stage of it as what we call a subgiant. It's decently brighter than a main sequence star of its mass should be. Not tons, not like an actual red giant, but the assumption is that this is an old star near the end of its life. That's been challenged more recently, but we'll get to that. Now, old for a star of this mass would mean creeping up on 3 billion years, and again, our own sun is 4.6 billion years old. Obviously, we'll be talking about alien artifact options near the end, but I want to drive that home now. This thing is around a star that's maximum lifetime would have caused it to die about the same time multicellular life was just coming into existence on Earth. And the thing in question is pretty hot compared to Earth, so it's not a great candidate for life to have originated at. So topic number 5. What natural phenomena might explain this, and why many of the suggested ones don't work well. It's too big to be a planet, but an object doesn't have to be massive to block a lot of light, any more than your curtains have to be heavier than a bowling ball just because they block more light. So the first couple thoughts were a lot of gas and ice, like comets. Comets are very small, but very bright after all, and thus block a lot of light. Or, alternatively, maybe a collision of planets that sprayed debris everywhere. Now remember, we've only seen this twice, so for instance a big comet coming in from deep space could have been spotted as it approached and 750 days later as it left, for instance. Ditto, it could have been a whole wave of comets perturbed in by some large body sweeping around it in the outer solar system. Tabby's star does have a red dwarf star about 800 AU from it. For relative comparison, Pluto is only about 1/20th that distance at 40 AU, and Alpha Centauri is over 300 times further away at around 250,000 AU from us. So that's a very plausible source of a sort of disruption that can cause a big deluge of comets. And debris spreads out but stays decently clumped on timelines of a couple years. Again, the first dip masked 15% of the star's brightness, and the second time 22%. So an expanding wave of debris would work. Such collision ought to be incredibly rare, so that it would be weird to luck out and see one. But we don't really know how rare, and it is the sort of thing you'd loosely guess happened every billion or so years, and expect the debris to hang around for decades. So watching 150,000 stars and seeing one is improbable, but not winning the lottery improbable. So of course they looked for evidence of either of those. We can't see the presumed conjunction of it with the star and us till May 2017, but any big debris field ought to be scattering light, and it ought to be emitting as much light as it absorbed. What is scattered and reflected plus what is absorbed would equal what is blocked, and even comets, which are quite reflective, absorb a lot of light. As we've talked about a lot on this channel, especially in regard to Dyson spheres and concepts of planet-wide cities, a Euclid-monopolis, light absorbed gets emitted as heat, in this case as infrared radiation in the general zone of about 10 microns wavelength, which corresponds to roughly Earth-like temperatures. Whatever hits an object in space and doesn't bounce away will warm that object until it reaches a temperature where it's radiating away as much as it absorbs. This equilibrium point has a peak frequency associated to it, and distributions of wavelengths around it that we can look for. Needless to say, those wavelengths associated to temperatures liquid water can exist at interest us greatly when looking at places where biological life might exist. We'd expect the debris to be glowing with all that light and quite brightly as these things go. Indeed, a planetary collision would glow a lot hotter too, since there's a lot of energy converted into heat in that sort of collision, the kind we think made our own moon. You also wouldn't expect an older star to have as many big collisions around it. Those get less common as time passes and debris clumps together and either gets into a stable orbit, falls into the sun, or gets ejected from that solar system. I've heard folks doubt the comet barrage options because of how much would be needed, but I'm inclined to reject that, even though it really would need to be a huge amount in this case, and I agree it isn't a terribly satisfactory answer. We don't know how much ice is hanging out in deep space near Earth, but Oort cloud estimates often routinely and largely exceeds Earth's own mass, and an awful lot of that is ice, so it doesn't seem that strange to me to think that this larger star might have even more than us, and that having a red dwarf only 800 AU away might cause a massive disruption. Heck, it could be a small planet passing by dragging a ton of stuff with it while it disintegrates. Pluto and most icy dwarfs are essentially oversized comets, but it doesn't look terribly plausible either. A really big asteroid belt could work. Asteroids block more light per unit mass than planets do, so an Earth's worth of asteroids, in terms of mass, would block a lot more light than us. But you'd kinda expect something like that to be decently symmetric. A ring, not a blob. And a ring doesn't have an orbital period making it block light every couple years for a couple days. It's always blocking light at that angle. But you could have a partial ring, a bit of a swarm of asteroids that moved in a pack. We see that with Trojan asteroid fields, for instance, and for that matter, a big planet like Jupiter could have really huge swarms of junk around it, sort of like Saturn's rings, and it could be tilted like Uranus's, so rings were perpendicular to the ecliptic, and blocked a lot of light. So what's left? Well, a planet forming would work, a protoplanet. It's not an ideal solution either, particularly since the star would presumably have to be a lot younger than it appears to be on initial inspection. But dating stars is harder than it sounds like, and we often do it by looking at the stars nearby it that it's moving with. That's not always the same thing, by the way. Stars often form from the same nebula and stick together in their movement throughout the galaxy, but many spin off, and packs of stars often plow through other packs of stars. Some of the stars in our night sky have been with us since the sun was born, and others are just briefly passing by. When we can see many moving more or less together, it makes narrowing down their age a lot easier. But moving into newer developments, Topic 6. We're not sure how old this star is, but if it is younger than we think, a protoplanet might work. Now, you can have planets form in star systems that aren't new. After all, if two ram together and explode, you expect some of that to coalesce back into a new planet eventually. So we could have a clumping debris field that already cooled in an older star system too, but neither of these feels too plausible either. We've also been looking at old photographic plates of this star. Again, catalog name or calling it WTF star or Tabby star are all very new. This thing was found over a century ago and well catalogued in different catalogs long before Kepler was launched. They've dug up over 1,000 old shots of that chunk of the night sky where this star is visible, and we can compare its brightness in those to the stars nearby it. Those indicate that since 1890 the star has faded by as much as 20%, though that has a lot of room for error. So again, what's left? Probably a lot of things. It might be one of these, it might be something new. We'll find out more between now and May 2017 when the event should occur again, and that will tell us a lot more too. We've been looking at it a lot with other tools, and again there is crowdsourcing to help get more funds for more tools. As this video comes out in August of 2016, we've got about 9 months to go before we'll get a lot more information and hopefully find out WTF. One of the other developments was SETI looking at it, and they didn't find anything. I don't think they expected to, but they had to try. No signals, but negative evidence is still useful to us. Now, folks often suggest aliens might use entirely encrypted signals, or not use radio at all, or use lasers instead of omnidirectional signaling. We talked about that in the Fermi Paradox Compendium, but the encrypted idea doesn't work too well for the same reason I don't need to break an encrypted code to know someone is sending messages. Particularly since if this is an artificial structure, it's as subtle and covert as an elephant blundering through a downtown metropolis. Encryption always has a cost, so you wouldn't encrypt everything unless you had a reason to, and if that reason was trying to hide your civilization, building a giant structure around a star that it noticeably eclipses isn't the best way of doing that. It would be like a sniper or recon force sneaking around the jungle in camouflage, but stopping every few minutes to fire flare guns and sing their national anthem through megaphones. Last topic. If this were a megastructure, what kind would it be? Well, it's not a Dyson sphere. If you're a veteran of this channel and the megastructure series, you obviously already know that. Now, a Dyson sphere doesn't need to be a rigid shell around a star. It actually shouldn't be, and originally wasn't meant to be when Freeman Dyson came up with the idea, but we've talked about that before too. It could be an early stage Dyson swarm that's maybe 1% complete, but that ought to be symmetric. You might build a Dyson swarm in stages, but you'd probably do it by making rings of swarm objects and adding to each ring, then adding a new ring. It's easier to do it that way since those swarm objects have virtually no escape velocity, and so you'd need almost no thrust to move from one place on the ring to a neighbor. Moving on the same ring of orbitals in a Dyson swarm could be accomplished with a spacesuit and a fire extinguisher. Now that said, every Dyson sphere begins somewhere, and if we were building one in our own solar system, it might start off as what I call a planet cloud, something we discussed a bit more in the Euclid Monopolis video a few weeks back. In that sort of case, you'd expect the home planet to basically develop a cloud of orbital habitats and solar collectors like a mini Dyson swarm itself, a big bubble, and to see rings stretching out from that initially. And that would look a lot like what we're seeing with Tabby's star. So I don't think this is what is going on at Tabby's star, but if it is a megastructure, that's what I'm putting my money on. Ditto, you could mine a planet in a similar fashion. You'd expect to see a big swarm of orbitals and megastructures near a planet you were strip mining, and a lot of debris too. Micrometeors aren't as big a deal when you don't have to spend thousands of dollars a pound for your space stations, because you can armor them up and surround them with ice and rock, as we discussed in the Rotating Habitats video. Considering the star appears to have dimmed in the century we've been observing it to, you could have a fairly symmetric distribution overall, except where some planets are that are being stripped for additional construction material. But here's the big problem. There's no reason to do this around this star. We're not seeing indicators of some sprawling interstellar empire in this region, and again, Kepler was staring at that patch of sky. A lot of those stars were nearer or further, but its neighbors were all in that sample. It stretches credulity that any intelligent life evolved around a star whose maximum lifetime is about 3 billion years. And again, while it's probably near the end of that, it might be younger too, which would make that even more unlikely. So this isn't someone's home solar system, and there's no sprawling empire there with other stars exhibiting the same effects. This gets us into motives. Why would you pick a short-lived star, one probably on the old side, as your one place to start setting up megastructures? You might mine inferior veins of ore, or farm not-so-fertile land, but not until you'd already gone for the low-hanging fruit, and there are tons of stars near that thing that are better candidates. Now, maybe they just got there a century or so ago, relatively speaking. It's 1,500 light years away, so what we're seeing now, in terms of it dimming in the last century and our current observations, all took place when the Roman Empire was falling. Maybe their home system is nearby, and it's not cocked our direction, and isn't a full Dyson swarm yet. Maybe they just started grabbing every system near them, and were only picking up this one as one of the earliest, and tilted at the right angle. But it does seem a stretch to think that it is either A, someone's home solar system, and they evolved very fast compared to us, or B, the sole place they decided to do this, or C, one of the first they did, and the only one we can see so far. Mostly because, even with C, it's incredibly improbable a civilization could be setting up interstellar empires in full-blown Kardashev 2 style, and be this close to us in space, and also coincidentally, this close to us in time, just starting, while no others are further along a bit further away. After all, if one civilization developed 1,500 light years from us, then if we drew a bubble of space 3,000 light years out, with double the radius and therefore 8 times the volume and 8 times the stars, you'd expect 8 more planets to have both technological civilizations on average. And 1,500 years is nothing on galactic timelines, so it would be really strange for one of those 8 not to have a much longer head start, especially since this solar system, if it was their home solar system, would imply 3 billion years is enough to become technological compared to our own 4.6 billion years. We talked about this general concept more in the Dyson Dilemma and the Fermi Paradox Compendium, so you might want to watch those to get a better idea of how ridiculously this would stretch the odds on plausibility if that's not settling home just yet. It would be like getting struck by lightning and winning the lottery on the same afternoon. So in summary, I don't see much odds for this being a megastructure, not just because it could be and probably is a natural phenomena, but because it just doesn't fit the bill. Okay, that will finish us up for the day. Some quick channel notes. The website should be up in a bit over a week, and we'll talk about that more next time, but what we have this week is the launch of the SoundCloud version of the channel, and that came out earlier this week, and I've been uploading more content throughout the week. It will still be a bit before it's all up there, but all the playlists will be up as albums when this video comes out. Except for Megastructures, which was my test, those each include an introductory segment to each playlist with some new material exclusively available in audio. SoundCloud is free to listen to, and I have enabled the download function so you don't need to be online to listen to them. In any event, that's up now, and there is some new content just for that format, and I might do some more that way since audio only is a lot easier to do than videos, and I never run out of topics. Speaking of that, next week's topic will take us back to the Existential Crisis series for a look at consciousness and identity, and we're going to examine some of the concepts like cloning, including duplication of the mind, hive minds, and distributed consciousnesses. Lots of familiar concepts from science fiction in there, and a lot of very strange ones, along with some disturbing implications. Last note, the plan is still in place to do about one video a month selected by an audience member picked by a raffle from the channel patrons. The intent is to do that via Patreon, but I'm having the darndest time thinking of a quick, fair, and easy method. I've noticed there are some online raffle sites that let you do something along those lines, but I haven't really had the time to investigate, and I feel like I've been putting that on hold too long. So if any of you have any ideas what would be best, head down to the comments section and I'll open a thread to brainstorm about it. YouTube doesn't have a pinned post option, so if you're having trouble finding it, resort by top comments, and hit the like button on the thread too to keep it at the top. And don't forget to like this video too if you enjoyed it, and share it with others. Thanks for watching, and have a great day.